I filled the bathtub with freezing cold water, and I sat at one side of the bathtub shivering, and then I turned on the really warm water on the opposite side, and sooner or later I was sitting in a bath of tepid water rather than freezing cold water. So there was a natural circulation. So that can account for some of the ability of these ocean currents to form. It's a way to distribute the warm energy of the sun from the equator to the poles. But that cannot explain everything that we see in terms of the strength of our current ocean currents or the past ones. And to have another idea, we have to look for the moon. So this is the second way that we get energy to get the circulation on Earth. Here we've exaggerated that. Here's the moon here, a lot closer in this diagram, and we're going to whiz the moon around. You see, that's the ocean with the moon. The energy comes from the moon. Slowly, its speed. The moon is gradually slowing up and moving further away from us. And it's that energy that is being transferred to the Earth and to the oceans. Okay, one other thing that you might have noticed if you were paying attention on this graph is this wild spike at 55 million years ago. I am not going to talk about this spike, other to say that carbon dioxide is not the whole story. You have been getting a simplified picture. This carbon spike is almost certainly caused by a sudden release, a cataclysmic release of methane. Okay, so here we have, what I was thinking of is that this would be cataclysmic and that species throughout Earth would be very negatively affected. So because biodiversity is a component of your grade 7 program, I thought I would look at some science articles. This is the publication Science. Fantastic publication, and our school gets it, so thank you very much for those who made that decision. Science has come out in the last few years with 2 publications looking at different species and their prevalence over from 20 million years ago to 60 million years ago. So the first are the spores and the pollen. So these are spores and pollen. And we can find these in Earth. These guys that wrote this article, they went to Venezuela and Colombia, and they dug down and they started to look for ancient spores and pollen. And this was the number of different types of spores and pollen that they found. That's between 20 and 60 million years ago. And I was surprised by this. First of all, you don't see a big response to this spike. The species continue to thrive through that. And the second thing is that there seems to be a slight correlation between high temperatures and there being lots of different types of pollen spores. Next, we're going to go to phytoplankton. So this is in the oceans, and this group published a paper, I think it was last year, in Science again, and this was the number of different types of phytoplankton. So it looks to me that being warm actually is beneficial for these very small creatures. We should not extrapolate that being warm is good for all of us. Motivating this lecture again, we wanted to learn more so that we could improve our computer climate models. So now it's time to take our historical view of the Earth and put it together with some physics. So I'm going to be very brief on the physics here. We're just going to look at basically what happens to sunlight whenever it enters the Earth. So 22% of it bounces off clouds. 20% of it is directly absorbed by the atmosphere. 49% is directly absorbed by the Earth. And about 9% of it is reflected from the Earth's surface. There's a bunch of stuff that goes on during the day. There's heat lost from the Earth, and there's transfer of heat from the clouds to the Earth. And this is kind of a cycle that goes on with a lot of energy. But the important thing is what happens both at night and at day How does energy escape? And this is how energy escapes. A lot of it escapes from the atmosphere. This is infrared radiation. So this is, you know that, what we saw early on. Let me see. Yeah. So this is a snapshot of some infrared radiation from that NASA spacecraft. So this is a snapshot of where that infrared radiation comes from. Most of it comes from the atmosphere. A lot of it comes from clouds, and a lot of it comes from the surface as well. Okay, so carbon dioxide is going to heat up the Earth, and we've already seen the effects of that. It will be to cover the Earth with a blanket, carbon dioxide blanket. So that's the idea. What are some of the things that aren't done well with current climate models? Number one, clouds. Very, very difficult problem to simulate clouds. Clouds are varied, enormously varied. Can you imagine trying to express mathematically what is going on with these clouds? When a cloud rains, when it doesn't, when it forms. These are incredibly tough problems, and they're very, very important to try to solve. Because, for example, these high clouds here, you can imagine that they reflect sunlight coming into Earth, but they also help protect help keep in heat. So they do two different things. They reflect the sunlight, but they also keep the heat in. Very difficult to figure out which one's more important in many clouds. Another thing that's done very poorly by present models are the periodic oscillations that we see both in the oceans and in the atmosphere. Very, very tough to get a handle on that. Some things we do understand very well. Absolutely easy to understand is carbon dioxide, how it reacts with light. Also, we can predict well into the future our planet's motion around the sun. So let's predict the future climate change. Here are several computer simulations. So this is only temperature. A huge simplification here. We haven't even touched on precipitation. But only temperature. This is based on a model where human activity is very economically driven. We are not environmentally conscious. Okay, so we see by 2100 that our average temperature rises from 14 degrees to roughly 17 to 18. I'm just going to go over the Intergovernmental Panel of Climate Change has come up with these statements. This is the definitive body internationally for making observations. I didn't like some of their early reports, but the 2007 report, which they came out last year, I thought was sounded pretty good and realistic, and I could have signed on to it. Here are their observations. Over the last 50 years, atmospheric concentrations of carbon dioxide and methane have become higher than any time over the last 650,000 years. The Earth is getting warmer. Most of this warming is very likely due to human activity. Whenever you see very likely in this report, it means about 90% sure. I think that's accurate. We are not 99% sure. 90% sure. In this century, sea levels will probably rise by 20 to 60 centimeters. Probably means about 66% or better. Okay? There will probably be an increase in droughts and hurricanes. The temperature could rise between 1 and 7 degrees Celsius. The reason for that weak last statement is that it very much depends on our responses to the problem. I'd like to say thank you to a few institutions, and number one, Wikipedia. What a fantastic resource. I just adored going through that. Second one is the book Climate Change, a multidisciplinary approach. I forget the author. I should have checked the author before I got on here. But this is a fantastic, well-rounded book. And lastly, I'd like to thank Masters Academy College for employing someone who is not a teacher. This is, I think, a very innovative and visionary idea. Thank you all very much.